All right, so let's back to the class. This is a magnitude comparator, and this is not used in computer actually. In the computer we use the arithmetic comparator, but uh, but this is good for the idea how the hardware compare a number. So later on we will learn how we design an arithmetic comparator. So before that we need to learn the this adder. So I believe you have been introduced to adder before in the previous course, especially the electronic course. All right, and the adder is very fundamental and very important in every digital system or computer, in your mobile phone, in your PC, laptop, and actually everything nowadays that contain a microprocessor inside. All right, and this is very interesting that we can design a hardware, all right, a circuit that can do arithmetic, especially adding number. All right, so when you give number 1, another one is 0, it can add the number 1 plus 0 equal to 1, for example, right? And that will be the fundamental of the uh, microprocessor that we have today. All right, so in this course we will learn how the concept is implemented in hardware. All right, and how to design that hardware using Verilog. So this is the idea of how we add numbers in hardware. All right, so again we need to go back to the fundamental one, which is a 1 bit. So how to design a 1 bit adder. Okay, so if 1 bit adder, we have only one input and two inputs, x and y, and we have output sum, which is the product of the addition. All right, and we have carry here, which is the carry if the addition produce a carry. All right, for example, when you add 1 and 1, so you have a carry. A carry. So this is the 4 possibilities of the output, carry and sum here. So for example, we add numbers 0 at 0, so we have, of course, the product is the sum is 0 and we don't have a carry. And if we add 0 and 1, of course we have sum equal to 1 and we don't have carry, and same as 1 plus 0. And if we add 1 plus 1, so we will have the product equal to 0 and the carry should be equal to 1. So these are the 4 possibilities of the addition, all right, for 1 bit addition. Okay, so if we have this 4 possibilities, 2 input, 4 possibilities, so we can create a hardware actually, all right, where we can design the circuit for this, starting from the truth table. So that sum and carry we can represent in hardware using this truth table. Alright, so this is the behavior of the adder. So from this, clearly we can see that carry, we look at the characteristic of this, and this is clearly that this is an AND gate. And 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, we have 1. This is exactly the AND gate. So we can get C with the AND gate like this. All right. And if you look at this is clearly a characteristic of the XOR gate, 0, 1, 1, 0. That's why we have sum is from the XOR gate. And this is the graphical symbol, and this we call the half adder. All right. So why is this half adder? Because it cannot be used to add a bigger number. So this one can be used for 1 bit addition only. So if you want to add, all right, more numbers, for example, yeah, something like this. A equal to 1, 0, and B equal to 1, 0, 1, and B equal to 0, 1, 1, for example, again. All right. So if we want to do this, we add 1 plus 1, we have 0, and we have 1 here, and here we have 0 and 1 here, and we have 1, 0, for example, again. Right. So by using half adder, we cannot do this, okay, because we have you see here you have 3 addition here actually from 1 1, 2, 3 addition. In this case we have only 2 input. Now we need to have 3 input in order to do this. All right, so that is why we need to have what we call a full adder. Okay, so this is an example multi-bit numbers. When we add multi-bit numbers, so that this one cannot be done using half adder. All right, because we need an extra bit, the carry from the previous addition. All right, the carries from the previous addition, C, to add to the current addition. All right, same like this one. So you need three input at least. All right. So to do that, we will have the what we call a full adder. So this is full adder, where this is the carry, all right, for this position, and these are the input Ci, Xi, Yi, Ci, Xi, Yi, and this is the sum Si. So we have another truth table. Now we have 8 possibilities because we have 3 input now. All right, so the number of possibilities is simply the number of input to the power of how big is the input. In this case, the input is 3 bit. So to power of 3, we have 8 possibilities, from 0 to 7. All right. So now again, we can get C, carry, and S like this. So how to get S? 0 plus 0 plus 0. Yeah. Hold on. Zero plus 0 plus 0, we can have S equal to 0 and C equal to 0. Okay, and 0 plus 0 plus 1, we have S equal to 1. We don't have carry yet. And again, when we plus 0 plus 1 plus 0, same. But 1 plus 1 plus 0, we have product equal to 0, but carry now equal to 1. right? In this case 0 1, in this case 1 plus 1 plus 0, so again we have carry equal to 1. And the last case, for example, is 1 plus 1 plus 1, so we have so 1 plus 1 plus 1, you have 1 and 1 carry, right? That's why you have sum equal to 1 and carry equal to 1. So again, when we have this equation, truth table, so we can have the Boolean equation and the circuit later on. All right, so this is how we get the Boolean equation. So S is actually X XOR Y XOR C I. All right, XOR C, and C, C here or carry here is X and Y, or X and C, or Y and C. All right, very easy. Right, from the K-map you can get the Boolean equation. So from the Boolean equation you can get the schematic. All right, so this is the schematic for S XOR all of this. You have S, and this is for carry. All right, so from that, yeah, we can actually create a bigger adder, and the name is ripple carry adder. So this hardware implement just like we did in hand calculation. So for example, we add X and Y. Yeah. So for example, we add X and Y. Okay, X, Y, and this is X1. For example, we have 0, 1, and this is 1, 0. Okay, so this is the position of, can you see that? Okay, so here all right, so for the first block here, for the first full adder here, all right, X this plus Y, X should be equal to 0, Y should be equal to X equal to 1, and Y equal to 0, and we have C0 here, or C in, all right, or C, the first C, because why we have this? Because our full adder circuit always has this extra input, right? So in this case, just like the comparator, we assume that the value is 0, so means that the carry from the previous block, so in this case should be equal to 0. Right, and because this is an adder, all right, so 0 plus 1 plus 0, you have sum equal to 1. And what is the carry? The carry should be equal to 0, right? So this 0 is this 0. And now to get S1, which is this one, this part, yeah, so you have X equal to 0 here and Y equal to 1. So you plus 0 plus 1 plus 0, 0 plus 1 plus 0, so you have 1 here. So here should be 1. And what is your carry? Your carry should be 0. So you see, we can implement the multi-bit addition using 1 bit full adder that we designed previously. All right, this one by connect the circuit like this. So if you have 3 bit, for example, all right, so you have another block, so it should be the same. Just connect like this until how many bit you want. You want 8 bit, you want 16 bit, you want 64 bit, no problem. All right, so you will have the output. So this is how we add a number in hardware, right? Any question? I think should be a very easy. All right, so now let's go to the next. Yes. Okay, good. So now, how do we model our adder using Verilog? So to model the 1-bit adder is very easy because we have the equation, right? So you can model using the data flow modeling, right? So this is how you model your full adder in Verilog. This is 1 bit, 1 bit. So you have your S, the equation is A XOR B XOR C, Ci, and C out here is A and B, or A and Ci, or B and Ci. Very easy. All right, so you can get the circuit from the equation, and this is by using the data flow modeling. And how we create a 4-bit adder. All right, so if we have 1-bit adder and we have the connection is like this, then should be no problem. We can use the structural modeling and of course use the hierarchical design methodology, where you use this small unit to build a bigger unit. All right, so this is 4-bit. So let's look at the connection here. The connection here. So maybe I draw a little bit so that you can see. Okay, let's go to this. Right, so for this one, what you can have is something like this. When you synthesize this one, you will have a block of full adder where you have this. The input is AB, the name is AB, and you have CO, okay, the output here, and you have one input called CI and one output called S. So this will be your block for this circuit. All right, now we want to create a 4-bit circuit. So again, we use this one. All right, so I may draw the circuit here. Okay, so we have A, B, C out, S, C in, like this, like this, like this. And we want to create a 4-bit adder. Okay, so I just have this one and just connect to this. Okay. And this one is connected to this. We have 2 bit now. And now we can have another bit become 3 bit. And the last one. Okay. And we have 4 bit now. Okay. So you see, when we use hierarchical design methodology, so we can create the bigger circuit using the smaller circuit. Yeah. And in this case, this one we call a new circuit. Yeah. In the new circuit, we call this as A3. This one is B3. This one is A2, B2, A1, B1, A0, B0. And this we call C out. And this one we call S3, S2, S1, S0. And this one we call CI. And this one we call, in this case, we call CI. This one we call C1, C1, C2, C3. All right. Okay, so now let's look at the code. How we write the code for this one. All right, using this one, and this one is 1 unit here, inside here, inside here, inside here, and inside here. All right. So in the bigger module, what we do is this. Okay, the name is adder 4 bit, and we have input CI, and we have input A, and we have how many A? All right, so we can group together later on, and we have B, 4 bit, and we have S 4 bit, and we have C O's here, C out. All right, now we define our input. So input here CI is 1 bit, so this is how we define 1 bit input. All right, and A and B we have A3 to A0, so that's why we have 3 to 0 A and also B. Okay, and for the S we have S3 to S0 as well, S3 S0, and output C CO. All right, 1 bit. And we also has internal wire, which is C1, C2, and C3. So this wire must be declared as wire. All right, so we have C3, C2, and C1. All right, so this is the declaration part. And how to create the whole circuit, connect everything together. So this is how. So we call the previous adder, the name is full ADD. So here, this is the name, full ADD. So that's why we have this full ADD. And the name for the unit 1 here is ADD 0. So we name this ADD 0. And the connection is like this. So CI, what is CI here? CI here must be this. And it is connect to where? Connect to CI in the smaller module. Alright, so you need to look at this, the arrangement of the port in your smaller unit. So the arrangement of the port for your smaller unit is CI. So this CI or this one must be connected to this Ci. And the next, this is A0. A0 must be connected to A in this smaller module. So that's why you have A0 here. And this is B0 connected to B here. S0 connected to S here. And C1 is connected to CO here. C1. So this will be the first module. And we want to add another module. So the module is the same, full add. Full add. And now we need to name it ADD1, for example. Alright. And the name here cannot be the same. Because this name represents this unit or module inside this full adder or adder 4-bit module. Alright. So again, now Ci in the smaller module here must be connected to what? C1 in the big module here. So that's why we have C1 here. And this is A1 connected to A, B1 connected to B, S1 connected to S, and the output here is C2 connected to C out in the smaller module, right? So that's why you have C2 here. And for the third one, the input is C2. That's why we have C2 here. And you have A2, you have B2, you have S2, and you have C3 here. All right. And for the last module, you have Ci. For the last module is C3, and A2, A3, B3, S3, and the output for the last module is CO. So that you have CO here. That's why you have this. Okay. Alright, so this is how you create the bigger circuit, the 4-bit adder, or even bigger adder, using a smaller 1-bit adder. Alright, this is a very good example of hierarchical design methodology and modularity concept, where we use or we reuse a previous design to build another design. All right. Okay. So now that is the adder. Now, how if you want to add or to do subtract? All right. Again, we need to think of the circuit that can do or can perform subtraction. All right. And to perform subtraction is not that easy because subtraction involves borrow, right? So for example, you want to do something like this. Right, in binary, if we want to do subtract, so 0 minus 1, so you need to borrow from the next bit here. All right, and to do that in hardware is not that easy, not easy. Okay, so it is a bit tricky when we want to do subtract. All right, addition is straightforward, we learned just now, but in the case of subtract, this is not easy. So to do subtraction, we need to learn the nature of Sine number in binary representation. So how we represent a Sine number in binary? All right, there are 3 different ways. For the first one, we call it a Sine magnitude representation. Okay, so you may have noticed, all right, where the negative number, to represent a negative number, so we just have look at the MSB, and the value of MSB must be equal to 1 to represent a negative number, and for the positive number, the MSB should be 0, and of course the MSB is used for what we call a sine bit. All right, sine bit, and the rest is the magnitude. So the first negative number that we can think of is that we can do something like this. If we want to represent, for example, our system is 4-bit system, all right, and we want to represent number 2, for example. So we can have the first bit MSB is 0, right? And we have this. This represent positive 2. What if we want to write or represent negative 2? So in this case, we just have the sign bit equal to 1 and the magnitude equal to 2. So this maybe can be used to represent -2, right? Okay, but this representation is not very useful because you cannot use in hardware subtraction. All right, so we need to invent another kind of number representation, maybe first complement representation. So what is first complement? So what we have learned is something like this. For example, yeah, minus minus 5, yeah. What we do is we take the magnitude of number 5, for example, 4-bit system. So we have 0, 1, 0, 1, and we complement the number. So we have 1, 0, 1, 0. So this is -5 in first complement representation. All right. So you see, now you have 1 here, means that this is negative number. All right. And the rest are the magnitude of 5 in first complement representation. Okay. So the good thing about first complement representation is that we can do something like this. So let's look at this example. First complement addition. Okay. So and again, the first complement is to represent a negative number, yeah, negative number. So let's say, for example, we have something like this. So number 5, number 2, both are positive, and when we add the number, we have positive 7, right? And in binary 4-bit, this is number 5, and this is number 2, and of course, when we add, we have 7, and the sign is positive, which is correct. Yeah, this is positive 5, this is positive 2, we add, we have positive 7. Yes, correct. Now, look at the second case. We have -5, and again, this is -5 in first complement representation. -5, first complement representation is this, because positive, just now, positive 5 is 1, 0, 1, 0, 1. So you change to first complement, you complement each bit. So you have 1, 0, 1, 0. That's why we have 1, 0, 1, 0 there. So when you add together, with positive 2, you have this number. And what is this number? This number is actually -3. All right, because when you complement this, you have 0, 0, 1, 1, and this is 3. You see? Meaning that by using first complement, we can do arithmetic for negative number. All right, and the interesting is that, look at this part. All right, +5 plus -2. This means positive 5 or 5 minus 2, right? Or in other words, we can use adder to do subtraction, right? Because 5 minus 2 is actually 5 plus minus 2. And plus here is an adder. And minus 2 we can represent using first complement number. Alright? So, what we can do is, this is 5, and we use adder to add with negative 2. This is negative 2 because 2 in binary is this. When you complement, you have 1, 1, 0, 1. Exactly this. Okay? So, when you add this number together, you have this. You have this. Right? And this is carry, you add again with this array, means that you use another adder, you add again, you have this, and this is equal to 3. And look at this, 5 minus 2 should be 3, and we have 3, meaning that we can do subtract using adder, but the sub one you need to use the first complement number. Alright, for the negative one. Same as this one. Alright, let's see. You have minus 5, this is minus 5, minus 2. So this is actually what we do. What we want to do is minus 5, minus 2. Alright, so we should have minus 7, right? The answer should be minus 7. So, again, minus 5. This is minus 5 in first complement number. And this is minus 2 in first complement number. And we use, again, adder, add this number together, so we have 1, 1, 1, 0, 1 here, and this carry we add again, use the adder, and we have this. What is this? This is of course negative, but we don't know yet negative what. So we need to complement this. We have 0, 1, 1, 1. So yes, this is negative 7 actually. Minus 7, and correct. So the conclusion is that yes, we don't have the subtractor circuit, but if we represent negative number in first complement format, we can do subtract using the adder. This is very good. Alright, you get the idea? Alright, do you get the idea? Please give feedback. Okay, good. Now the problem is that you see here when the number is positive, when the result is positive, or in this case, not positive, sorry. In this case, we don't have carry, right? So if we don't have carry, the result here is the result that we want already. But if we have carry, we need to add that carry to the result to get the correct result. Alright? If not, the result is not correct. Meaning that you need to add 2 times here. Add 2 times means that you need two adder. So that will make your circuit a little bit bigger. Alright? Because you need 2 adders. What if we can do addition using second complement number instead? Alright? So same concept, but now the negative number is represented using second complement number. What is second complement number? All right. To get second complement number, for example, number 2, yeah, in decimal is 0, 0, 1, 0. So to get minus 2 is, or second complement for 2 is, you need to complement to get the first complement, which is 1, 1, 0, 1, and you need to add with 1, right? Add with 1, and you can get the second complement. 0, 1, 1, 1, 1. All right, so 1, 1, 1, 0 is the two's complement for number 2. Okay, so let's now we do subtract or do addition using the second complement. And again, second complement is only used to represent a negative number. All right. Now, using the same number here, 5 plus 2. So this is positive 5, this is positive 2. You plus, you get positive 7. Should be no problem. And this is minus 5. And this is minus 5 representation in two's complement. And you add 2. All right, and you get this minus 3, and this is minus 3 in two's complement representation. All right, minus 3. And now the interesting part is this. All right, again, 5 plus minus 2 means that 5 minus 2. All right, and the answer should be 3. All right, and again, this is 5 in base 10. All right, and this is minus 2 in second complement representation, and when you add, you get this number, and of course you have one carry, but this carry can be ignored in hardware. You can ignore in hardware this carry because this is bit number 5 already. So your system is 4-bit only, so look at the 4-bit. So the 4-bit 0011 is exactly 3. All right, and same with this one. Okay, minus 5, minus 2. All right, minus 5, minus 2. So this is minus 5, this is minus 2. All right, you add together, you have minus 7, and this is minus 7, 4-bit, and this one is ignored. So when you see this, by using second complement for addition, you no need extra adder, just like what you have or what you did in first complement addition. All right, so meaning that by using second complement addition, we don't need an extra hardware. In other words, extra adder here. All right, means that our circuit will be at least 1 time smaller than the first complement representation. And this is why in the computer that you have, we will use the two's complement representation instead of first complement or sign magnitude representation. So remember, in the computer, negative number is represented using second complement representation. All right, so that's why when you have your calculator, for example, okay, let's look at this example. Look at your calculator if you have calculator. In this case, I use the computer calculator. All right, let's see. Okay, can you see the screen? So when we change to programmer mode, so that we have number representation here. So let's say you negative 2, right? So negative 2, negative 2. So try to change this negative 2 to binary. Okay, so actually you have here already. So this is in binary. Can you see this? I cannot zoom. Yeah, so if you have the calculator, for example, this is my calculator. Okay, so this is my calculator, my phone actually. So I have app for the calculator, the scientific one. So if you have the Casio scientific calculator, you can use that. Let's have a negative number, minus 2, like this, and try to change to binary base. And what you get? You'll get this, right? And because the size of the calculator is quite big, this is not 4-bit. So let's take the 4-bit one only. 4-bit, the most left, right hand side. The 4-bit from the right hand side. So the number must be, right? If you take only 4-bit, so must be 1110, correct? From your calculator. Let's see. Right, from your calculator, if you can see here, you see 1110, 1110, 4-bit. The rest just ignore, because this one is very big calculator. How many bit? This is 64-bit, I think. Yeah, and this is negative number. So minus 2 for 4-bit is this. So now you change to try to change to convert this. This is second complement number. Convert this to decimal. So you have 0001. You plus 1. You have 0010, right? So in positive is actually number 2. So you have this. Means that in computer or in your calculator, the negative number is represented in second complement number, and this is for 4-bit. If 4-bit positive number is like this. What if your system is 5-bit? So negative 2 in 5-bit is this. You just extend the sine bit to the next, to the MSB one. All right. So this is bit number 0, 1, 2, 3, 4, bit number 4. Right? If your system is 6-bit, so you just extend the number 1. And this is actually minus 2 as well. So if your system is 8-bit, all right, so this is minus 2 as well. And if your system is 12-bit, this is your minus 2. As simple as that. All right, and remember, in computer or microprocessor or in your calculator or any digital system, minus 2 will be always this, using a second complement representation. All right, so we will use a lot later on, in our design. Okay, so you need to understand this. All right, so that will be the adder and the subtractor already. And for that, meaning that we can design our subtractor using an adder, means that with adder you can have two functions actually. First, you can have adder. Second one, you can have subtractor in the same circuit. So that's why in computer normally we have what we call the adder subtractor unit. So this circuit can do add and do sub based on this control signal. So when the signal here is equal to 0, so it will do add. And if the signal here is equal to 1, it will do sub. So I will explain this later. Alright. Okay, so with that, thank you very much. See you tomorrow.